Welcome to the Henry AI Labs walkthrough of Keras code examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. In this video, you'll learn how to process three-dimensional volumes. Compared to the usual two-dimensional height by width by RGB images, we're now using three-dimensional height by width by depth CT scans where we have voxels instead of pixels with their own respective voxel intensity range compared to the 0 to 255 pixel values that are usually used for RGB images. So we'll see how to process this data, how to implement a custom data augmentation loop. We'll see how to visualize these CT scans looking at height by width snapshots. Then we'll look at the three-dimensional convolutional network using 3x3x3 kernels, seeing the resulting parameter explosion by doing this high-dimensional tensor processing. Then we'll train the model and then see how we can evaluate it on a single image with these three-dimensional CT scan volumes. The next example is 3D image classification from CT scans. The key difference here is previously we've looked at images represented as height by width by RGB tensors. Here we're also using images that have a depth dimension. So CT scans, the medical images, they rotate around and they take a snapshot of height by width and they rotate around such that you get the whole depth reconstruction in these medical images. So you have a height by width by depth volume really. So it's also different how they store the pixels. So here they store pixels as they're called voxels in this case of using this volumetric data. So this is going to be the best walkthrough I can. Honestly, these 3D image classification isn't really something that's super common in the deep learning literature. So we begin with the usual imports, noting the only thing that's different from the past examples is that we're now importing zip file. So compared to doing the exclamation mark flag for a shell command to unzip these files, you can also use the Python zip file library in order to unzip files within Python. So another thing to note about the original code where we're getting the data set is that it's also common to see a lot of these data sets hosted on GitHub. So you use this URL, same syntax as the previous example, image classification from scratch, how we use this URL, and then you can use keras.utils.getFile file name. So this is how you use Keras to do like a web request to get a file into the local repository. So then we use the OS library to make a new directory for this medical data that we're going to be putting these CT scans in our current workspace, which you can index by clicking on the folder icon in the collab workspace. So in this example, we're kind of treading in uncharted territory with these three-dimensional images. So they're going to use a new kind of encoding format. They say this nifty format with the extension .nii. So we're going to have to use a new kind of Python package, ni-babel, in order to read in these images. So this is describing the raw voxel intensity. So these values range from negative 1024 to above 2000. So compare this with, say, our RGB pixels that range from 0 to 255. We have a different range for each, the set of each values that it can take in our height by width by depth, like data object. We have a much broader range than 0 to 255 in this range of different voxel intensities for this completely different kind of image than usual, say, ImageNet images or MNIST or the most common kind of things in computer vision. So in this block of code, the author is going to be implementing custom functions to normalize and preprocess this data because we're using these 3D images. We can't rely on the Keras preprocessing to do things like rotation because rotation is basically you multiply a matrix by another matrix, but now we have a completely differently shaped matrix or a tensor. So we need to have our own custom way of rotating this three-dimensional CT scan. So this first line of code uses our new ni-babel library in order to load these files from the file path that we've gotten these file paths from this GitHub link, and now it's talking about traversing this MOSMed data directory and getting to this study0001.nil.gz. So we read that and then we get into the normalization. So normalization is where we're trying to take these raw voxel values from -1000 to 400 and normalize them so that they're in the interval of 0 to 1, because this is much more compatible with our deep neural networks. So we have the explicit minimum value is -1000, maximum value is 400. So we index the volumes, and then we, if it's less than the minimum, we set it to be the minimum. If it's greater than the maximum, we set it to the maximum. This is just how we loop through each of these three-dimensional objects and make sure they really are contained within -1000 to 400. And then we do the normalization. So this is the standardization normalization technique, where you take a value subtracted by the minimum and then divide it by the maximum minus the minimum. And this is how you set all the values on the scale of 0 to 1. And then we convert it to the float 32 data type in order to input it for our deep neural networks. So now we're going to resize the volume. So this is a really important factor for the computational complexity consideration. So say these were like 256 or 1024 by 1024 by 1024 as well. So we have this gigantic three-dimensional image. Well, you can't really process that unless you have like a supercomputer and you know, like all this crazy expensive machinery to deal with that. So we have to resize these images to be 128 by 128 by 64 so that we can process them with our convolutional network. So it gets the current depth by indexing the tensor. Note how we do image.shape -1, really -1 because it's 3 dimensions is just the same as doing 2, I think, unless you have, say the batching is already integrated with this, but really you're just indexing the image.shape. So this image object is going to be our 3-dimensional volume. So image.shape at 0 is the width, image.shape at 1 is the height, and then at 2 is the depth. But here's another way of accessing this. So now we're going to divide it by the desired depth, width, and height, and then we have our rescaling factor, and then they use this ND image library in order to implement a custom rotation to this object, and then also a custom zooming to this object. So another common practice when organizing these datasets for deep learning is to have explicit folders for each of the class labels. So in this case, CT-0 consists of normal lung tissue images, no sign of viral pneumonia, because these are COVID CT scans. CT23 has these ground glass opacities that are what they're trying to detect when they look at these CT scans and try to diagnose COVID from these images. So this is one way of setting this kind of file structure up for input to Keras. So note how we have normal scan paths equals the os library.path.join, get the current directory, and then the link pointing to CT-0, and then within this list we loop through each of these individual things, like say study 0001, 002, and so on, and then we do the same thing to construct all the paths for the positive or negative examples where we do have the COVID pneumonia. And then we also just print this out to get a sense of how big our data set is. So we have 100 normal lung tissue CT scans and 100 abnormal tissue scans. So right off the bat, we notice that obviously this is a really small data set for the sake of deep learning. So now that we have this list of the different paths that index this file structure, we're going to use the process scan function, where in this process scan, we wrap up the read the file function, we wrap up the normalization, and we wrap up the resize the volume, all into these 3 sequential function calls to take in an input path like mosmetadata /ct/0 /study/0001, and then turn it into our 3-dimensional height by width by depth with the normalized voxel intensity with each slot in that 3-dimensional volume. So this is the syntax, np.array, looping through each of these paths and then processing them such that in the end we have abnormal scans, which is going to be our NumPy array containing these 3-dimensional volumes. So now we're also just constructing a NumPy array. Again, we have a binary classification problem where CT/0 stores the normal CT scans, and then 1 is the viral pneumonia scans induced from COVID. So now we do this explicit indexing for the training and validation sets. We're going to set aside 70 of each, so we have 70 examples of the pneumonia and 70 examples of the normal cases, and then 30 for validation. We just explicitly index this list by doing this :70 or 70 : for the validation set. So as mentioned previously, we only have 100 examples of abnormal CT scans and 100 examples of normal scans, amounting to 200 total examples for our data set. And then further, we're splitting away 60 of these for our validation set. So one of the keys to deep learning is to prevent overfitting with data augmentation, especially when working with computer vision, because we have all these great priors that we know to encode into the image augmentations. Like we know that these CT scans, they should be semantically invariant to these rotation angles, as well as usually things like horizontal flipping and like slight translations, brightness intensities. These are the kind of things that we use with data augmentation. But in this example, we're going to stick to rotation. So in this example, the authors are using the SciPy ND image library. The scientific Python library has already implemented a rotation for these volumes. Because again, rotation, if you have a height by width pixel map, is different from if you have height by width by depth, because you basically take a matrix and then you multiply it by another matrix is how you can rotate it in the same kind of matrix space. But aside from that, so we're relying on this previous implementation of rotation in this ND image library. So we define our array of angles. This is the magnitude of the data augmentation. We're not going to be rotating it, say, a full 90 degrees. We rotate it between -20 and 20 degrees at these fine-grained intervals of 20, 10, 5, 5, 10, and 20. So we randomly sample one of these angles. Then we rely on this SciPy implementation to rotate our volume. Then we, again, I think this is just another check maybe on the rotation, but we want to keep our values in this range of 0 to 1. So now that we have our augmented volume, I think what this does is the tf.numpy function, I'm not exactly sure, but I think this is about appending this to our computational graph. So the TensorFlow has this numpy function, SciPy rotate, which we've defined right here, with our volumes and our TensorFlow.float32. This is the data type for this. So this tf.numpy function, this might be if we're concatenating this operation with our model. And this is with respect to one of the original topics we discussed in this video series on whether we want to pre-process our data on the CPU or on the GPU. So this looks like we want to pre-process this on the GPU, and we're going to append it to our computation graph such that we just pass in the raw volumes, and then it's going to get rotated and apply the data augmentation as a part of the model on the GPU. So now we wrap this into our train preprocessing and our validation preprocessing loops, which we're going to, as we peek ahead, we're going to later put into the .map of our train data set, which is an object. This is the TF data object that we'll get into next. So we're going to define our data loaders, the train loader and validation loader, that pipelines these three-dimensional CT scan volumes into our model. So we use this syntax of the tf.data object.dataset.from tensor slices. So from tensor slices sounds really fancy. The way I understand it is that we have our X train, Y train, which remember we previously loaded by indexing these file paths and processing them with our functions. So basically we have these, we have a NumPy array of these volumes. So from tensor slices, I think it just means really passing in the NumPy array and nothing fancier than that. But so we have this tf.data object, and this is, I think, the primary data loading object in TensorFlow and Keras. So we have this train data set, and we're going to construct this object by making it a group of these operations from this tf.data object. So we take our train loader, which we define with this tf.data.dataset.from tensor slices, passing in our volumes and our NumPy array of the 0, 1 class labels, and then we chain it with, first we shuffle the data so that it's not going to be completely in order where, say, the first batch is only normal examples and the next, and it processes this until it's only processing the ones and the zeros because of the way that we've sequentially ordered the way we load this and put it into our NumPy array. So we shuffle the data first, and then we're going to do .map train preprocessing. So this is where we stack on this preprocessing function that we've defined to apply to each volume. So it takes in a volume and a label as the arguments, which it's using to map from this data object, X train, Y train. It's indexing each of the volume label pairs, and it's applying these functions to it. It's rotating it, and it's expanding the dimensions on the volume on the third axis. So I'm not exactly sure why it adds the channel here, but I think it probably has something to do with the compatibility of these batches for the input to the deep neural network. So then we use the .batch with the batch size. This is the, so this is, I believe this is all happening on the CPU actually. So it looks like what we're doing is we define this to prepare the data on the CPU before it gets into the model. So this is our pipeline of preprocessing the data on the CPU before it gets to the model on the GPU. So previously I had said that it looks like we might be putting this as a part of our computation graph, particularly this function had that kind of, it had that kind of look to it. Like we're going to put this as the input layer and then put it right into the augmented volume thing. But really it looks like this tf.data thing is about processing this on the CPU and then pipelining it into the model on the GPU. With this trained dataset variable that we've defined, we can use the .take1 syntax in order to sample from our dataset. So here we're going to visualize an augmented CT scan. So we see an example of the CT scan dimension 128 by 128 by 64, and then we've expanded the dimension 1. We did this, okay, so this is the, you do the TensorFlow.expand dimensions volume axis equals 3 in order to have it be -1 like this. Otherwise it would just be 128 by 128 by 64, but we want this explicit 1 at the end of it for the sake of batching it and putting it into our deep neural network. The same idea is the simple MNIST convnet, where originally MNIST is 28 by 28, but we want to expand the dimensions to have this additional 1 to explicitly note the grayscale. And this isn't quite grayscale, this is something like voxel intensity. But so what we're doing here is we take this data, we sample this data from the .take, and this returns a batch of our data. So we index 0 from this batch so that we can just visualize one of these images. Now we convert this image to a NumPy array, and then within this set of images, so it's a depth map. So we have this height by width by depth. So we can index that with 0 to get a height by width slice of our depth. So we could also turn this to be 1 to get another slice of that depth map. But in this case, we're going to stick with 1. So we see the dimension, and then we plot the image and see this first example of the CT images that we're working with, a slice of the height by width of it as we're working through this three-dimensional volume. To further illustrate this concept, this is a montage of the slices. So this is what it looks like as you continually index this position indexing on the three-dimensional volumes as we loop through and get a height by width snapshot of each of these different planes in our three-dimensional map. So all this code is doing is it takes the original data, it's going to apply the rotation to it, transpose it, reshape it. All this is just making it compatible for looping through it with respect to these for loops that put this into our matplotlib.plt subplots in order to construct this grid of maybe 8 by 4 images in our visualization of the montage of CT slices. So now that we've prepared this data for our deep neural network, we're going to define a three-dimensional convolutional network. Three-dimensional convolutional networks are often used for these kind of volumetric objects, as well as sometimes they're used for video data where you treat the time axis like it's a depth dimension, and then you apply these three-dimensional convolutions for things like, say, action detection in video data sets like UCF 101. So the key object here and the key difference between, say, just a basic convolutional network is we're using three-dimensional convolutions. What this means is instead of sliding a 3x3 filter, we're sliding a 3x3x3 filter across these feature planes in this image. So it's very similar to any other convolutional network that we'll see throughout these tutorials. We have the same kind of idea where the 3x3x3 convolution downsamples the spatial resolution as well as the depth resolution. We see in the first layer going from 128 by 128 by 64, 64 is the depth, to 126 by 126 by 62. And then again, the max pooling operation where we slide this two-dimensional kernel. Well, it says max pooling 3D, but you can see by the decrease in the spatial resolution that really it's still a two-dimensional, like say clustering, where it's taking the max of the neighborhood of 2, but it's just 3D in the sense that it's applying it to this depth axis as well. And then we also see the number of feature planes we have throughout this neural network going from 64 to 128 to 256. And then in the end, we flatten out this entire feature map into a dense vector and then map it into our class output, which is the 1-0 classification of whether it's a normal CT scan or a viral pneumonia instance of CT scan. So another interesting detail is we have the activation is sigmoid. A sigmoid activation is going to automatically put it between 0 and 1 compared to the softmax, which is going to put a probability density on both of the output classes. And then we need to do numpy.argmax to sample the actual prediction from the model. So overall, we visualize our model. We have 1.3 million parameters, even in this simple neural network. So already this picture right here should tell you the story of three-dimensional objects for deep learning. We already have 1.3 million parameters with a simple, say, 3-layer neural network with these pretty low resolution input images. So you imagine the high resolution original image that comes out of a CT scan machine, processing it with something like, say, a vision transformer or a ResNet or these massive architectures would require a lot of computational power. So now that we've loaded the data and defined the model, we can finally apply our model.fit and train the model. So one quick change I made to the code, if you know with Keras models you have this verbose parameter. 0 is silent, which means it won't output anything at all. 1 will give you this progress bar, and 2, which it originally was set to, will just give you an output bar at the end of every epoch. But for our sake, we just want to run this one line because this is the time on the CPU. So note we had about 25 minutes per step. So now we're going to go back and switch the runtime to the Google Colab GPU, rerun all this code, and see how much faster it processes this on the GPU. This will probably be the first case in our examples where it's just significantly faster because we have a 1.3 million parameter, 3-dimensional convolution. This is going to be way faster on the massively parallel GPU computing compared to the CPU. So now we're rerunning this code on the GPU. Note how much faster it's going through each epoch. Right off the bat, 30 seconds for the first epoch, then 25 seconds, compared to 30 minutes when we're running this on the CPU. And this speed up is largely because we're doing these massively parallel convolutions on this GPU. It's a much faster speed up than compared to, say, like a recurrent network or something like that, where you wouldn't see as dramatic of a speed up when using the GPUs compared to the CPUs. And we also have 1.3 million parameters, so we're starting to play around with kind of big models that really benefit from the GPU acceleration. So some of the code in this, we have a initial learning rate. We have a learning rate schedule. Learning rate scheduling is one of the techniques that are used to train deep neural networks, where you might start at saying have this really small value for the learning rate, warm it up such that the model has this curriculum of how much it updates its parameters. Sometimes it has a high learning rate where it makes a sharp update, and then sometimes it has the same gradient direction, but it hardly changes its parameters. So these are concepts like weight decay and decay rate. These are all these ideas of having some curriculum, meta learning control of the learning rate in the algorithm. So same kind of idea behind the model.compile, checkpoint, at the end of every epoch, it'll save its weights in our directory as 3D_image classification. It'll only save it if it's the best it's seen on the training set, or it might be the validation set, but it has some criterion for saving the best. And then it has early stopping. So early stopping is a technique. Say we've decided to train our model for 200 steps and we're going to leave the computer and go do something else while it does this massive duration of training. Well, if it's not improving anymore, early stopping is going to stop the runtime. So in Google Colab, we have free GPUs, but they'll still time you out if you try to do something like run it for 2 days straight and leave. The Google Colab will kick you out for doing that. But imagine that you've graduated from Google Colab to now you're paying for Google Cloud runtime. Well, if you're doing that and then you're paying for this time, you definitely don't want to be running it and paying for it when it's not even improving the model. So that's when you use something like early stopping. So then we have all the same syntax. We pass in the callbacks in order to do the checkpoint and the early stopping for our model. And then with all this, it starts training the model. So we've run this model for about 20 epochs to save time with respect to doing this. So interestingly, when we get from epoch 18 to 19, we start to see the validation accuracy actually start improving. So we go from 50% validation accuracy, which for balanced binary classification is just random guessing. And then all of a sudden at epoch 19 and then 20, we finally start to see improved performance on our 60 images of validation set. So the author of the code notes that we only have 200 samples. The full data set of over 1,000 CT scans can be found with this link. When they train it with 100 epochs, they achieve 83% accuracy. Here we've achieved about 67% using only 20, and then there's a variability based on how you randomly seed the data set. Because remember that we're doing this manual indexing of our paths to set train and validation splits, and we don't have it's like a random, because we do just dot shuffle. So we don't have a completely disciplined way of splitting the data set and achieving the same exact performance every time. And this is really important for experimentation. So then I had a quick issue and I wasn't able to fix it, but so one thing you can do is you plot the training curve. So you see how at each epoch it returns the accuracy and the loss. So a common thing to do is to plot these things, but I think there's been some change. I'm not exactly sure of the syntax, but so originally the code was just this model.fit, and then the author had indexed model.history.history with the metrics for the training accuracy and loss. And then I tried what you used to be able to do is you do history equals model.fit, and then you'd run this code and then it'll be stored in this history object. But I guess the history object, looking at the Keras documentation, it seems like it's just for explicitly setting the parameters during the training or something like that. So unfortunately I wasn't able to get this, but hopefully I can just quickly tell you about the motivation behind this code is to plot out the curves of the training set loss and the validation set loss. And it's important to try to make sure these things are increasing together or decreasing together, and not just the training loss is decreasing and nothing happens to the validation accuracy, which would indicate overfitting. So now that we have a trained model, we load the weights from our best weight, where we have this callback snapshot that loads the 3D image classification.h5 at the end of every epoch. So we load these weights, and then we use the model.predict, and then we use this expand dimensions in order to input a single image to our model. So now we use the scores. Again, we use this 1 minus thing because we're using a sigmoid activation. This is different from using a softmax activation at the end, where we do scores equals np.argmax for the individual prediction, or we just do scores equals like prediction at 0, prediction at 1 in order to index the two softmax probability densities. So this is the density it puts on this one individual image, classifying it as an abnormal CT scan. So to quickly recap some of the things that we've learned in this video, we've seen how three-dimensional convolutions are defined, how we define a three-dimensional convolutional network, and how this differs significantly from what we usually use in computer vision, which are these height by width by RGB images. Here we're using height by width by depth CT scans in order to detect viral pneumonia in this kind of data set. So we've seen how you normalize this kind of data, how you have this voxel intensity, which is significantly different from the pixel values, and how we normalize it, how we have to define our own rotation. In this case, luckily we have the SciPy implementation, which would save us a lot of time with doing this, how we load the paths and pipeline this using the tf.data object and get this with the shuffle the data, map it with the preprocessing, batch it up, do this on the CPU to get it into our model. We've seen how you can visualize these height by width snapshots of a three-dimensional volume of CT scans. We define our three-dimensional convolution. We noted how we have a lot of parameters for a relatively simple model due to the dimensionality of these tensors that we're processing. We've trained the model. We saw a massive speed up with the GPU. Unfortunately, some problem with the history object, but then we saw the evaluation of how you make a single prediction on a three-dimensional volume.